Hi all. In the last class we have seen how to represent permutation as a product of transposition, and using the number of transpositions we have used to represent that permutation, we can identify that is a product of odd permutations or product of even permutations. And we have proved a theorem about that idea, which states that no permutation of Sn, finite permutation group Sn, can be expressed both as a product of even permutation and as a product of odd permutations. That means once you represent sigma as a product of odd number of transposition, that is always, or that sigma has represented sigma can be represented as a product of odd permutation, this always contains that odd number. Okay, so that means if you start with sigma belongs to some S6, say sigma is equal to 1 2 3 4 5 6, and I write this is some this is 4 goes to 5, 5 goes to 1, and 2 goes to 6 goes to 3, and 3 goes to 2. So this is one of the permutations in S6, and first of all we can write this as a product of disjoint cycles. We start with 1 goes to 4, we know that 4 is mapped to 5 and 5 is mapped to 1, so that that represents one orbit. And we start with 2, you can get another one. 2 goes to 6 goes to 3 goes to 2 again. So the sigma is a product of two cycles, two disjoint cycles, two disjoint 3 cycles, and each 3 cycle can be expressed as a product of transposition. So first one can be written as 1 5 into 1 4. When you multiply these two transposition, you will get this one. And similarly you can write 2 6 3 as 2 3 into 2 6. So now you can see this sigma is a product of 4 transpositions. So this is the way we write sigma as a product of transpositions. So once you write the sigma as a product of 4 transpositions, so that contains even number of transpositions. So this every expression of the sigma as a product of transposition should contain an even number of 2 cycles or transpositions. That is what we have proved in the last class. Using this idea, we can classify an arbitrary permutation in Sn as even permutation and odd permutation. Okay, so if we start with a sigma belongs to Sn, okay, where n is greater than or equal to 2, obviously, otherwise we cannot consider transpositions. So if you consider a permutation in Sn for n greater than or equal to 2, then you can define even permutation. What is an even permutation? Even permutation is nothing but sigma is a product of even number of transpositions. Even number of transpositions. Transpositions means 2 cycles. Okay, so for example, the sigma is a even permutation, and now we can define odd permutation. The definition of odd permutation is nothing but it is a product of odd number of transpositions. So odd permutation, sigma is even permutation, sigma is even permutation, sigma is odd permutation if sigma is a product of even number of odd number of transpositions. Odd number of transpositions. So this is the definition of even permutation and odd permutation. Obviously identity is an even permutation, because identity permutation can be written as 1 2 times 1 2. So this is a product of, or you can write, there are so many expressions. We have already remarked that this expression is not unique. So once you write I as 1 2 into 1 2, then it is always an even permutation. So identity is always contained in even permutations, set of all even permutations, and we call set of all even permutations as An, and set of all odd permutations as Bn. Okay, so these are the symbols used for denoting that odd permutation and even permutation. So if obviously we can say that I belongs to A, and if we choose any two say sigma 1 and sigma 2 belongs to AN, then you can say that sigma 1 is a product of even permutation and sigma 2 is a product of even permutation. That means if sigma 1, if you write sigma 1 as tau 1, tau 2, etc., tau k, where k is even, and we can write this sigma 2, that is always a even permutation, say gamma 1, gamma 2, etc., gamma m, that is also even, m is also even, because these two are elements of AN. Now what is sigma 1, sigma 2? This shows that this is a sigma 1, sigma 2 is nothing but tau 1, tau 2, etc., tau k, and gamma 1, gamma 2, etc., gamma m. So obviously this k plus m, it contains k plus 1, k plus m transposition to represent this sigma 1, sigma 2. So k plus 1, k plus m is even, because these two are even. Therefore we can say that sigma 1, sigma 2 is also an element of AN. So if we choose any arbitrary two arbitrary even permutations, then product of that is again an element of AN, or that is again an even permutation. So we can say that this AN has this closure property. Okay, so AN has closure property, so we can put this AN has closure property, and has closure property, and obviously permutation multiplications are associative. So we search for identity, we can easily get I belongs to AN. And if sigma 1 is a we write sigma 1 is an element of, or sigma is an element of AN, then sigma can be written as tau 1, etc., tau 2, etc., tau k, where k is even. K is even. Then how will you write the inverse of this? What is sigma inverse? Okay, we know that if we choose any transposition, say AB, we can say that AB is always identity. Okay, so for a transposition, the order of transposition is 2. When you multiply it 2 times, then you will get identity. This shows that the inverse of AB is AB itself. Okay, or order of AB is equal to 2 means inverse of AB is AB itself. So every transposition has its own inverse. Okay, so if tau is a transposition, then tau is the inverse of tau itself. Okay, so what is sigma inverse? If you write this these transposition in reverse order, tau k, etc., tau k minus 1, etc., tau 2, tau 1, then when you multiply sigma inverse, you can get tau 1, etc., tau k, again tau k minus 1, etc., tau 1. But we know that this tau k is identity. Okay, so in the next step we can write this as identity element. So similarly you can cancel all these, so you will get identity, which shows that the inverse of sigma is nothing but tau k minus 1, etc., tau 1. So this is the one of the applications of this representation. If you write a permutation as a product of transposition, then you can easily write the inverse of that permutation. Okay, you need to write just write the transposition in the expression of sigma in the reverse order, so that will give the inverse of that sigma. Okay, so which shows that if sigma contains an even number of transposition, then sigma inverse also contains k number of transpositions. That means even number of transpositions. So whenever we write sigma is an element of AN, then this sigma inverse is also element of AN. Okay, so this enables us to define this AN as a subgroup of SN, because it contains all the properties of, or all the it satisfies all the axioms of this subgroup. Okay, so here we can conclude that AN is a subgroup of SN, and this subgroup AN is called alternating group. Okay, so AN is called alternating group. This subgroup of SN is called alternating group. and it is denoted by an. Okay, so this is the interesting subgroup of this Sn. Now we can calculate the cardinality of this an. If Sn is finite, if n is finite, then Sn is always contains n factorial elements, and we will find what is the number of elements of this an. Okay, so first of all, for that we consider Sn for n greater than or equal to 2. Then obviously this Sn contains at least one 2 cycle or transposition, say 1 2. So 1 2 belongs to Sn. Okay, now we define a map from an to bn, say lambda tau. So that means this lambda is depending on this tau. So if you fix any ODE permutation, or if you fix any one transposition, so you can write this map. Lambda tau is a map from an to bn. Okay, so it is defined by lambda tau of sigma. Sigma is an element of an, which is equal to tau sigma. Okay, so this is the definition of this map for all sigma belongs to an. So if you choose any sigma from an, then sigma contains or sigma is a product of even number of transposition. So when you consider this expression, then we adjoin one transposition to the sigma. So if sigma contains even number of transposition, then tau sigma contains an odd number of transposition. So obviously this sigma, tau sigma is an element of bn. So this defines a function from an to bn. Okay, and if we consider this lambda tau of sigma 1 and lambda tau of sigma 2, if these two quantities are equal, then we can say that tau sigma 1 equal to tau sigma 2. Using the cancellation law, since this is a group, you can cancel this tau. Since Sn is a group, then you can cancel these two things. So we will get sigma 1 equal to sigma 2, which shows that lambda tau is 1 1. So it's a 1 1 map. Similarly, if you choose any, let any gamma belongs to this bn, if you choose any arbitrary element from this odd permutations, then you can define put sigma is equal to tau gamma. Okay, then what is this lambda tau sigma? Lambda tau sigma is lambda tau of sigma is tau gamma, so that is equal to tau times tau gamma, and tau square is identity because tau is a transposition 1 to 1 to 1 to identity, so this will give gamma. Then this shows that for any gamma belongs to bn, there exists a sigma which is in an, because since gamma is odd permutation, then if you adjoin one transposition to this, then you will get this is a product of even number of transposition. So sigma belongs to an such that lambda tau sigma of lambda 2 of sigma is equal to gamma. Okay, so from this you can write lambda tau is onto. Okay, so which shows that there is a 1 1 onto map from an to bn. Clear? That means the number of elements of an and number of elements of bn are the same. So if you consider Sn, we know that n factorial is the cardinality of Sn. So this denotes the cardinality, and we know that this an union bn is nothing but Sn, because if you choose any sigma from Sn, then it is either an odd permutation or a even permutation, and we know the important theorem, no permutation of Sn can be expressed both as a product of even and a product of odd. That means if we consider an and bn, then this an bn partition this Sn. Okay, so this will be empty and an intersection bn will be empty. So cardinality n factorial is equal to cardinality of Sn, and cardinality of Sn can be written as cardinality of an plus cardinality of bn. But from this fact, there is a 1 1 onto function from an to bn, we can say that these two cardinalities are the same. So this is 2 times cardinality of an. Then cardinality of an is nothing but n factorial divided by 2. Okay, so the total number of even permutations in Sn is nothing but n factorial by 2, half of the total number of elements of Sn. Okay, so this is given as a theorem, theorem 9.20 theorem. The statement is, if n is greater than or equal to 2, then the collection of all even permutations of the symbols 1, 2, 3, etc. n forms a subgroup. We have already proved that subgroup of order means cardinality, order n factorial by 2 of the symmetric group Sn. Symmetric group means Sn. Okay, symmetric group Sn. Okay, and this subgroup is called alternating group. Okay, so this is the end of 9th section. The next class we will continuing the discussion of section 10 onwards. Okay, thank you.